Okay, here's a thought. What if the solution to, well, our growing energy needs was literally falling from the sky, delivered by the clouds above? Today, on the Deep Dive, we're exploring the really intriguing world of generating electricity right from raindrops.
Yeah, our mission is to unpack some recent, pretty amazing scientific breakthroughs that are turning, simple rain into a potential powerhouse. We're going to be drawing on insights from some top sources, journals like Nature, articles from Science Alert, City University of Hong Kong, Coffee Table Science, and Climate Cosmos. So get ready for a deep dive that might just reshape how you see a simple shower. We're looking at the ingenious engineering turning tiny raindrops into miniature power plants. How exactly are scientists pulling this off? I mean, what's the secret? How do you get real usable power from something like a single drop of water?
Well, what's fascinating here is that for years, the challenge wasn't just getting any power, it was getting enough to be practical. Previous attempts, incredibly inefficient. But this new breakthrough, this is a massive leap forward, truly.
Massive. We're talking several thousand times more efficient than what came before. It's really a fundamental re-engineering of how you capture that energy, moving beyond just tiny static zaps to, well, efficiently harvesting a significant usable current from each drop. That's the real paradigm shift.
Oh, okay. 1,000 times. That efficiency leap is, yeah, astounding. So what is this ingenious tech? What makes such a dramatic difference?
The core of it lies in a new droplet-based electricity generator, or DEG for short. The research team, and this was a big collaboration, Professor Wang Zhuangkai from CityU, Professor Zheng Xiaocheng from University of Nebraska-Lincoln, Professor Wang Zonglin from Beijing. They really cracked the code. They focused on two crucial factors. First, they used a special material, polytetrafluoroethylene, PTFE film. Exactly, similar family. It's what they call an electric material.
Yeah.
Think of it like it holds a charge almost permanently, a quasi-permanent electric charge. So as water droplets keep hitting this PTFE surface, the charges on the surface interact with the water, and they build up, accumulate. This was key because it smashed through a previous barrier, this bottleneck of low charge density that really limited older designs.
Got it. So more charge builds up on the surface. What's the second factor?
The second factor is this really clever design. It's like a specialized gate or switch that the raindrop itself activates. They call it a field effect transistor, or FET-like structure. So the device has two conductive paths, an aluminum electrode and an indium tin oxide, or ITO, electrode. And that charged PTFE film, it's deposited right on the ITO.
Okay.
Now, when a falling droplet hits and spreads out, it momentarily connects these two paths. It bridges them. And that creates a closed-loop electric circuit. The droplet acts like a resistor, the PTFE coating is like a capacitor, and bam, all the stored charge on the PTFE gets fully released, like a sudden, powerful surge of electricity.
Right, like flicking a switch and discharging everything at once.
Precisely. And this is a huge improvement over, say, conventional droplet generators. Many older ones relied on the triboelectric effect.
That's like static electricity, right? Rubbing a balloon.
Yeah, basically. It creates charge, sure, but it's not very efficient for getting continuous usable power. This new DEG, with its FET-like design, it just blows past that. It achieves an instantaneous power density. Get this, up to 50.1 watts per square meter.
Wow.
That's thousands of times higher than devices without this clever architecture.
So by engineering these surfaces and the structure, they've turned the simple impact of a raindrop into a really powerful electrical pulse. And the beauty is, it's tapping into something fundamental, kinetic energy from gravity. So the energy source is inherently free and, well, endlessly renewable.
Exactly. Free and renewable. And what's more, their research shows the efficiency isn't really affected by lower humidity. And crucially, both rainwater and seawater can be used.
Seawater, too. That opens up huge possibilities. Coastal areas.
Absolutely. It broadens the potential application significantly.
This really does sound like a game changer. Okay, so what does this all mean for us, in the real world? Where could we actually use this tech beyond the lab?
Well, potentially anywhere water hits a solid surface. I mean, think about it. The hull of a boat cutting through water.
Right.
The inside of your water bottle as you move it. The top of an umbrella in a downpour.
Never thought of my umbrella generating power.
Or integrated into coastlines, maybe surfaces of ferries. The potential for just ubiquitous energy harvesting is immense, turning everyday water interactions into power generation.
It sounds like every little detail matters here. The materials, the surface textures. You mentioned material science playing a role. Things like piezoelectricity.
Oh, absolutely crucial. Advanced coatings, surface treatments, especially ones that are super hydrophobic, meaning they repel water strongly, or just hydrophobic, they're vital for optimizing how that droplet hits, spreads, and releases its energy. You want to minimize energy loss from water just running off, maximize the interaction.
Makes sense.
And yet, researchers are even using microstructures, nanoscale designs, basically texturing the surface to maximize the contact area, squeeze every bit of energy out of that impact.
Okay, so they're refining the small scale. But what about scaling up, moving from lab prototypes to something that could, I don't know, power a town eventually? That seems like a huge leap.
It is a huge leap, and that's where things like the bridge array generators or bags come in. These were developed by a single university. Think of them like solar panels, but designed specifically for raindrops.
Oh, and like solar panels.
Exactly. See, one big challenge is connecting lots of small generators together without losing power at each connection. It's like wiring tiny batteries, you get losses. Bags are designed as one integrated system. This solves that connection problem, making the whole array much more efficient.
How much more efficient?
Well, the research suggests these bags have nearly 5 times higher peak power output than conventional large area raindrop devices of the same size.
5 times?
Yeah. And that kind of capability is absolutely vital if you're aiming for, megawatt level output, powering serious equipment.
This brings up a really intriguing question I saw in the sources. Could they actually generate more power than solar panels by 2030? That sounds bold. Almost impossible.
Well, it sounds bold, doesn't it? But let's unpack that a bit. You have to look at the limitations of current solar tech first. Most solar panels, they hover around 22% efficiency. The best cutting-edge ones might hit 24.3%. And that's actually getting close to the theoretical limits for silicon. Beyond a certain point, about 86%, the physics means you start generating mostly heat, not more electricity.
Okay, so there's a ceiling approaching for solar efficiency.
Pretty much. And then there's the obvious weather dependence. Solar panels on a cloudy day might only produce 10–25% of their normal output. During storms, they're essentially useless.
Right. And that's exactly where raindrop energy flips the script. Our sources say it's just getting started with efficiency gains and its big advantage. It works at peak capacity during storms, precisely when solar panels are offline.
Exactly. It creates what the researchers call a perfect complementary system. Solar for sunny days, raindrop generators for storms.
So it's like having a backup power system that actually gets excited about bad weather.
You could put it that way.
Yeah.
And that's why 2030 is being floated as this potential magic year. Several factors are converging.
Like what?
Well, first, massive demand. Global renewable capacity needs to triple by 2030 to hit climate targets, like IRENA's 1.5 degree C scenario. That's over 11,000 gigawatts needed. Huge market pull.
Okay, demand is there.
Second, costs. Manufacturing costs for these devices, these 10Ns, triboelectric nano generators, they're dropping fast. Unlike solar panels, which need, rare earth elements, complex processes, 10 inches can be made from pretty simple stuff. Common polymers, electrodes, even recycled plastics.
Much simpler materials.
Yeah, which means the cost per watt could potentially drop below solar much faster. Plus, installation costs could be minimal. You could integrate them into existing roofs, roads, structures.
Interesting. What else?
Then kind of ironically, there's climate change itself, increasing rainfall intensity in many regions. That actually provides more raw material, more potential energy for these systems.
Right, more intense rain, more power potential.
And the timeline fits. Researchers are aiming for prototypes within the next 5 years. That puts commercial deployment right around 2030.
Wow. And you mentioned some impressive power records earlier. What was that figure again?
Yeah, one prototype, just 15 by 15 centimeters square, reached a peak power output of 200 watts per square meter.
200 Bellini to, how does that compare?
Well, to put that in perspective, that's often more power than many conventional solar panels generate on a cloudy day.
More than solar on a cloudy day. From raindrops.
It highlights the untapped potential. And that power density is how a single tiny drop, 100 microliters falling just 15 centimeters, can generate that startling 140 volts.
Enough to light 100 small LEDs. That really is the aha moment in action.
It is. Now, of course, it's crucial we acknowledge the challenges. This isn't a magic bullet just yet.
Right. What are the main hurdles?
Well, the big one is the variability of rainfall. Frequency, intensity, it fluctuates wildly. That makes it tricky for a dependable, constant electricity source.
Sure, you can't guarantee rain.
Exactly. And because rain is transient, the captured electricity needs effective handling and storage. You need good capacitors or, more likely, batteries.
Storage is key.
And then there's always cost effectiveness on a large scale, ensuring these systems can genuinely compete with or complement other renewables affordably.
Okay, challenges noted. But,
Yeah.
and this is where it gets really interesting. How are they actually tackling these issues?
Yeah, the solutions are actively being developed. For rainfall variability, they're looking at integrating real-time weather data, meteorological forecasting with smart grid systems, kind of like how wind farms use forecasts to manage output, predictive energy management.
Smart grids, okay. What about storage?
Well, the rapid advances in battery tech are huge here,
Yeah.
especially things like solid-state batteries. They're becoming much better suited to handling intermittent power sources like this, storing those sudden bursts effectively. And energy management systems are getting smarter too, figuring out how to smoothly integrate this kind of power into the existing grid.
And reliability, how do these hold up?
That's potentially a plus. These raindrop energy systems generally have fewer moving parts than, say, wind turbines, potentially more reliable, lower maintenance.
Mhm.
And think about it. Unlike solar panels that can degrade in the sun or get smashed by hail,
Right.
these Tang devices are literally designed to withstand impacts. That's how they work.
Mhm.
Falling objects are their fuel source, not a threat.
Ah, good point. Designed to take a beating.
Mm.
And it's not just theory, right? You mentioned they've actually powered things already, even small scale.
That's right. It's happening now. The sources mentioned successful demos, like lighting up around 80 LEDs powering a clock. Another test used rain-like droplets through a tube to light 12 LEDs.
So the proof of concept is definitely there.
Absolutely. It shows the potential. You could genuinely imagine, down the line, umbrellas charging phones or maybe boat hulls powering their own navigation lights.
It really turns the idea of getting caught in the rain from just an inconvenience into maybe a power-up opportunity. So as we wrap up this deep dive, it's really clear that raindrop energy is, well, it's a noteworthy and developing challenger in our ongoing search for clean, renewable power. The idea that the pitter-patter on your roof might one day be the sound of your electricity bill shrinking, it's becoming less science fiction and more, well, plausible science.
Exactly. And if you connect this to the bigger picture, those converging market factors around 2030 are key. You might see an oversaturation in the solar market, actually. Manufacturing capacity for solar is projected to far outstrip deployment by then. That naturally creates openings, opportunities for alternatives like raindrop power.
Ah, market dynamics playing a role too.
Definitely. And governments. They're increasingly looking for diverse renewable portfolios, not putting all their eggs in one basket. Grid stability, energy security, diversity helps. So the vision is moving from micropower, these small demos, towards megawatts. And that happens through deploying multiple D10Gs simultaneously in these massive arrays, just like solar farms.
It's really fascinating how often potential solutions to huge problems like energy come from looking at something incredibly common, something we barely notice, like rain, in a totally new way. It makes you wonder, doesn't it? What other hidden energy sources might be waiting out there in our natural world, just waiting to be unlocked, transforming things we once overlooked into essential power for a more sustainable future? How might thinking about this change the way you listen to the next rain shower?